You know about this. We'll wrap up considerations which relate to material for which you are responsible on tomorrow's quiz with what we talk about at the top of the hour. Wrapping up our considerations in regard to writing equations for Bronsted-Lowry acid-base reactions. Construct PSIs. To do this, you must pay attention to the chemistry that occurs when the system in question is prepared. Now, regarding PSIs, I noticed an error in what I showed you last time. Oops. I forget this pointer thing. I'm just getting used to doing all this modern technical electronical stuff. You see up top, right side of sodium chloride, pure substance, where I wrote in Na plus and Cl minus? In ink, see that? NaCl, like any ionic compound, is not a species. It is a substance, but it's not a species. So, the fine point to recognize here is that when you write a PSI, a principal species inventory for an ionic compound, you write the formulas for the ions of which the compound is composed, because those are the species in the compound. NaCl does not represent a species. It is not an integral substance, as is a molecule or an atom or an ion. We have to be specific with the language if we're going to succeed in communicating successfully. So, PSI for an ionic compound, just recognize the ions of which the compound is composed. Of course, this obligates you to recognize when a formula is in fact for an ionic compound. So for now, we'll just abide by the general rule of thumb which I expect you were programmed with in 2045. What rule of thumb do I refer to? When you look at a formula, if the formula is for a material that's composed of a metal and a non-metal, like Na, metal, Cl, non-metal, you can expect it to be for an ionic compound. There are all kinds of exceptions to this. Let's not worry about the exceptions now. As opposed to a formula which is composed exclusively of non-metal atoms, like H, hydrogen, Cl, chlorine. That material we shall expect to be molecular. And for the most part, there are no exceptions to this rule of thumb regarding the recognition of molecular compounds, except for ammonium ion compounds. Because ammonium ion, H4N+, is an interesting cation. It's the only common cation which contains no metallic elemental components. So when you look at a formula like H4NCl, you have to recognize that this is an ionic compound composed of ammonium ion and chloride ion. So you see this H4N as part of the formula. You should know that. Now, I'm going to post a copy of this on the Sakai website so that you can download this, because it does sum this stuff up on this inventory business in a convenient fashion. Also, I noticed on this, regarding our previous conversation, that some of the QPSIs I had were not quite on the money regarding component water. So I edited this sheet. First case, 100 milliliters of 1 molar HCl. Since hydronium ion and water molecule are essentially identical in size, if we take chloride ion to be the same size as a water molecule, then we can recognize why QPSI regarding water for the 100 milliliters of 1 molar HCl will be on the order of 5.3 moles of water. Now you can't see what the asterisk refers to yet, because again I'm learning about this and I've now realized I can make this thing really small on a Xerox machine, or I can word process it to be really small, because with this nice gadget I can blow it up all I need. Consequence, from now on I'll try to make these so that the sheet of information that I wish to project to you will be contained in its entirety on this thing. Then we'll want to focus on a particular set of information in the sheet, and we'll expand it. Now, weak BL acid, 100 milliliters, 1 molar acetic acid, 1/10 of a mole of acetic acid in the 100 milliliter sample, and about 5.2 moles of water. You remember when we talked about the size of an acetic acid molecule and argued that, gee whiz, we'll say it's about equal in size to 3 water molecules. That's where we get that PSI. And then, when we get to the 200 milliliters of 1 molar K2S, we're starting to get blurry here. See what you think about this 10.5 moles of water as my QPSI for water. I'll let you think about that one. And now you see what the asterisk refers to. Do you agree with the QPSIs given above for water liquid? That's what this is about. Now I don't think we should need this anymore, so I'll cut this off. Lynn, pull the screen in front of the projector beam, please. I've also discovered that if we turn off the projector beam and then we want to go back to it, it takes about 2 to 3 minutes to warm up. I hope the department replaces this with a better system. That's why I block off the projector beam rather than turning it off. Okay. And so we proceed. We finished last time with part D of question 1810 and recognized the consequence of adding water to the aluminum nitrate solution. In the system under consideration, water is the strongest base in appreciable amount, and hydrated aluminum ion the strongest acid. So the acid-base reaction expected to take place by adding water, by diluting the aluminum nitrate solution, is in fact a reaction which involves the conversion of hydrated aluminum ion to more hydronium ion and the conjugate base of hydrated aluminum ion, which is pentaquo hydroxo aluminum plus 3. I don't care about the name. We'll talk about the name stuff at the end of our conversation this term, chapter 24. That's a long way off. Again, I say to you, when we need to converse about a chemical substance or species, the simplest and best way to do it is write the formula for the stuff. So part E is what happens if we evaporate solvent from a water solution of a weak acid or a weak base. Well, we have to, number one, recognize, or re-recognize, since we've already pointed this out, in any water solution of weak acid or weak base, since the solute acid or solute base reacted to a limited extent with water, not 100% extent, in this water solution of the weak acid or weak base, always there exists equilibrium between the solute acid, water as reactants, and for the acid, hydronium ion and conjugate base of the acid. for the solute base, weak base, base plus water, reactants, double arrows, hydroxide ion, and conjugate acid of the reacting base. That's the principal acid-base equilibrium existing in the water solution of the weak base. So what impact do we exert on such an equilibrium when instead of diluting, we evaporate solvent? Well, it's really the reverse of what we looked at regarding the dilution effect. For system E, we're considering acetic acid solution. So, we start by realizing at the instant at which you begin to remove water from the system by evaporation, the equilibrium is killed. And you didn't add anything new to the system. So the change which will occur to reestablish equilibrium is either this reaction proceeding as written left to right or in the opposite direction, right to left. What happens? Right to left, because we took this stuff away. So here's what goes. And if we apply the rule of thumb that the reacting acid, in this case is hydronium ion, is a stronger acid than the product acid, extent large. All right, we go to F. Potassium hydroxide solution and sodium bicarb solution. Here I've written the inventories. We'll go down here for equation writing. There's the inventory. Pick me out the strongest acid. Directive. Look at your acid-base table. I've got the info sheet. You may have in your hands the info sheet or the acid-base table from the notes. Either one will suffice. And when you examine the materials listed in the acid column and the materials listed in the base column, you'll see that, on occasion, a particular species has its formula contained in both columns. Do you see that statement applying to this inventory? You see that the formula for hydrogen carbonate ion, commonly called bicarbonate ion, is contained in the acid column as well as the base column. There are really a fair number of species which have this property of being a stronger Bronsted acid as well as a stronger Bronsted base than water. But most of the time, like hydrogen sulfate ion formula, that is a much stronger acid than water. But it's not a stronger base than water, it's a weaker base than water. Which, of course, the acid-base table tells you. As we would expect, because hydrogen sulfate ion is the conjugate base of the strong, potent acid, sulfuric acid. Okay. But hydrogen carbonate ion is an interesting critter, again, because it is a stronger Bronsted acid than water, as well as a stronger Bronsted base than water. Well, with that, we recognize that for system F, the strongest acid in our PSI is what? Hydrogen carbonate ion. Again, we're just using the information in our acid-base table as a crutch. Now, if you do this as many times as I do, you'll see this table in your sleep. To me, it's relaxing. I'm happy to see the table in my sleep. At this stage of the game, if you see the table in your sleep, you'd probably be in horrors. Ah! I can't get away from chemistry. And the truth of the matter is, you can't. A living system is a marvelous system composed of all sorts of neat, interesting, and important chemistry. So even though you may not wish to think about chemistry, we could make the argument that in ways chemistry is always thinking about you. Strongest base? Okay. Reacting acid, reacting base. This thing gives H plus to this thing. So we wind up with water liquid is the product acid. Carbonate ion is the product base. Remaining task, assess extent. Large or small? This acid, stronger than this acid. This base, stronger than this base. LG, shorthand for large.
Excuse me, I'm just a little confused about the acid. Like, when hydrogen bicarbonate, it turns into a stronger base. So,
Wait. What's this it that turns into a stronger base?
hydrogen bicarbonate?
This is an acid.
But it's constant bases.
So what? You don't compare acid strength to base strength. You compare acid strength to acid strength and base strength to base strength. All right? Now let's look at system G. Notice that for system G, well, what you see in the notes is potassium hydrogen carbonate. I changed the formula to sodium hydrogen carbonate simply because I want to demonstrate this system. And in our laboratory, we have on the shelf sodium hydrogen carbonate, 0.5 molar. We don't have potassium hydrogen carbonate. Who cares? Because neither Na plus nor K plus form well-defined hydrates. Consequence, adding K plus or Na plus to a water solution has no impact on pH, unlike adding these multi-charged ions which form the well-defined hydrates. All right? Strongest acid. Now we're looking at this inventory with that inventory. What's the strongest acid this time? Hydrogen sulfate ion. And again, this formula, as with this formula, I write these to keep with structure. If I write the compact formula for this, HCO3 minus, and ask you for a structure picture, you're probably going to connect hydrogen and carbon. That's wrong. If I use the compact formula, HSO4 minus, you're probably going to connect hydrogen to sulfur. That's wrong. I don't want you to make those mistakes. You know, after this stuff becomes a fixed part of your chemistry vocabulary and you want to use the abbreviated short formula or the shorter formula, that's fine, but not now. Let's get it structured. And now, for G, what's my best base? Strongest base? Bicarbonate ion. So the main difference between F and G is that in F we see bicarb ion behaving as an acid, but in G it's going to behave as a base. And it has the capacity to do either, since the table reminds us that this interesting species, or interesting because it is a stronger Bronsted acid as well as a stronger Bronsted base than water itself. All right? Now, in writing these reaction equations, I usually write the formula for the product acid before the product base, because that's the way I start with reactants. But this time I'm going to write sulfate ion first. Which is the product base of this reaction. And transfer then to get the product acid H plus to this formula. Now look at the table. The Bronsted lauryl acid base table. You see this formula? Do you see the information that's in the table attended to this formula? This is not true carbonic acid. It's hydrated CO2. When you bubble carbon dioxide in the water, for example, to make seltzer water, studies show that just about all the dissolved CO2 turns into hydrated CO2 rather than true carbonic acid. Further studies show that true carbonic acid, which we'll talk about in greater detail a little bit further on into this chapter, true carbonic acid is an acid which is about 1,000 times stronger than hydrated CO2. But since over 99% of the dissolved CO2 converts to hydrated CO2 rather than true carbonic acid, it follows that when we bubble CO2 in the water, what we get in the main is hydrated CO2. That's why I have the quotes on the formula. If I take away the quotes, we're talking about true carbonic acid. Now, do you see other information regarding this stuff? Or let me ask you this question. Have you ever had the experience of shaking a can of warm soda pop or warm beer and then popping it open? What happens? Explodes? Well, to a degree it does. But I don't think it explodes to the extent of removing you from the Earth's surface. But it will explode to the extent of spraying fizz on you. Because this hydrated CO2 is not very stable. The bonds between water molecules and CO2 molecules, which must form to make hydrated CO2, are not very strong. They're easily broken. And when these bonds are broken, hydrated CO2 converts to water, liquid, and CO2, which you might recognize to be the reverse of what we just told you about, chemistry-wise, that occurs when you make seltzer water. You bubble CO2 in the water, you make this stuff. If you got the seltzer water warm, you shake it up, take the cap off the bottle, and you're going back to this stuff. Tell me, under normal laboratory conditions, what phase is exhibited by this stuff? Gas. Is this stuff particularly soluble in water? Why not? Non-polar. But this is not only quite polar, it's hydrogen bonding. So from an electric lightness standpoint, water molecules bond much stronger with each other than they do with CO2 molecules. Upshot, CO2 is not very soluble in water, as opposed to, for example, something like ammonia. You can make 16 molar ammonia solution. You can still smell the potent odor of ammonia over the solution, but you can dissolve ammonia in water at very high concentration, even though ammonia by itself is also a gas under normal laboratory conditions. But ammonia, like water, is quite polar and also a hydrogen bonder. So electrically, they're very much alike. So getting ammonia to dissolve great quantities into water is easy, but not CO2. So with what we have on the board, I'll ask you to make a prediction. Or here I wrote OBS question mark for observe. Beaker. Here's the sodium hydrogen carbonate. Let's pour a good slug of sodium hydrogen carbonate, half molar, into the beaker. And now I ask for you to predict the observation that you're going to make as I now add an equivalent quantity of sodium hydrogen sulfate, half molar. What prediction do you make on the basis of what we have here considered? Oh! All over the place. A little bit of a mess, but who cares? Alka-Seltzer. Now, one remaining system, H. Sodium sulfide, we recognize, number one, this is what kind of a compound category-wise? Ionic or molecular? Metal, non-metal. ionic. And the ion components, the species of which this stuff is composed, Na plus, S2 minus, sodium ion sulfide ions. But we notice from the information on the acid-base table that sulfide ion is what?
Strong base.
Strong base. Now, that means when sodium sulfide is dissolved in water, something happens beside dissociation. The dissociation of the lattice puts sodium ions and sulfide ions in the solution. But do the sulfide ions just sit there in the presence of water molecules? No. They react with water to create what species? Hydrogen sulfide ion and hydroxide ion. Hydrogen sulfide ion being the conjugate acid of sulfide ion. And the extent of this reaction is practically speaking what? 100%. So we get their inventory for sodium sulfide solution. Sodium ions, hydroxide ions, hydrogen sulfide ions, and water. And here again is a somewhat novel ionic compound because it contains no metallic components. But it does contain ammonium ion, whose formula by now you should be quite familiar with. So the species inventory for this is ammonium ion and chloride ion for the salt. But I'm talking about a solution of this. Well, this salt dissociates like all ionic compounds do when they're dissolved in water, giving me a solution that's rich in ammonium ion, chloride ion, and water. Question?
For this one, G, what's the extent?
What is that?
With G, the extent was large, right? The previous one.
Oh, yes. With that copious bubbling, I think we surely proved that it's large. You know, but with the analysis of strength comparisons, we know it's large. Okay so far? So tell me. Strongest acid? Ammonium ion. Strongest base? Extent? If you made this mixture in the laboratory and put your nose over the beaker in which you made the mixture, would you well expect to detect an unpleasant, acrid odor? The odor of ammonia. Now, do you see that for this system, in front of 1 molar ammonium chloride, I wrote this. What's that mean? Excess. Excess means this is in great abundance. Consequence, in the notes we are telling you for this system that you are to write 2 equations. So you got to pay attention to quantity. This parallels what you had to do when we responded to part C of this question. The sodium hydroxide solution, sulfuric acid solution mixture. Okay, because if the ammonium chloride solution is in excess, ammonium ions are in excess. So this reaction goes large extent, which means it effectively clobbers hydroxide ion, and since the ammonium ion is in greater mole quantity than hydroxide ion, it practically speaking, this reaction clobbers all the hydroxide ion. So after this is now removed from the inventory, this is another trick of sorts. Not a trick, really, it's a good bookkeeping practice. When you have to consider more than one reaction for a system, and you've got the PSIs written, pay attention to the reaction which you have just considered and recognize what components of the inventory have been eliminated? We eliminated hydroxide ion by this reaction. And now you re-examine the inventory. What other acid-base reaction can we expect to occur in this system? Well, back to the game. What now is the strongest acid? Still ammonium ion. What now is the strongest base? I'm listening. Look at the table. Who said ammonia? That's good. Because after this first reaction ran, we now have ammonia in there in abundance. So we're going to look at another detail of this inventory game. And recognize that when I rewrite question H, I have to change this to 3 equations. 3 equations, not 2. Let me make a note for myself right now. I'd meant to do this, I forgot, but now we're at this, and my memory has been jogged. 3 equations. Ha-ha. If we play by the rules, we recognize that at this point, from a PSI standpoint, I have a system which is still rich in ammonium ion because it was originally added in excess, and I now have an abundance of ammonia. I made it by this reaction. This reaction was large extent. And at this point, the strongest acid is still ammonium ion, but now the strongest base in abundance is this stuff. What are the products? The products are ammonium ion and ammonia. But does this reaction in fact occur in this system? Did we not write a reaction equation which at this juncture shows the giving of H plus from the strongest acid present to the strongest base present? Hey, you bet this goes. But does this reaction really amount to something we have to pay attention to in terms of system composition? Does this reaction change system composition? No. But does it occur? You betcha. Occurs. Does not delta for change. System shorthand for composition. All right, so since I have now, by your thought-provoking considerations, changed for this the requirement of writing 2 equations to 3 equations, we realize that at this juncture, after we consider this reaction, ammonium ion is still that strongest acid in the system in appreciable concentration. And what other base? HS minus. Because in making this mixture, we are bringing together ammonium ion with HS minus. This reaction will make hydrogen sulfide and ammonia. Anybody familiar with hydrogen sulfide from a toxicity standpoint? from an aroma standpoint? I'm just curious. Rotten eggs, yes. When eggs rot, they make that stuff. Have you ever heard about one of the most unfortunate uses of hydrogen cyanide? Gas chamber gas. That stuff is more toxic than hydrogen cyanide. Fortunately, because you're going to deal with some of that stuff in 2046 Laboratory, Assignment 7, Horrors. The human olfactory system is so sensitive to that stuff that it can detect it, the human olfactory system, on parts per billion. That's not much. Not a harmful amount at all. But the result of this detection is that you go, ooh, rotten eggs, I go away. Because it smells bad. Reaction extent? Small or large? And now we have it.
Is there any extent to the second equation?
Extent? This one?
Yeah.
What do you think the extent is? I'll bet you can tell the exact extent. The same. We recognize that it does take place. What is that? You talking about this? Go ahead. Go ahead. We'll talk about a system like this when we talk about buffers, but we asked about extent. What do you think is a fair extent to apply to this?
The extent is 0, right? Because the forward...
If it's 0, then it's not going.
Well, it's going, but the forward happens at the same rate as the reverse, right?
Oh, I understand that. But what's the extent?
Then it's 100. It just goes straight.
Well, I'll let you muse on that. I would argue that the extent is 50%. But the extent is really meaningless. Because we recognize that if one of these reacts with one of these, or a million of these reacts with a million of these, it still doesn't change the system composition at all. So how can we determine extent, really? And now we have placed ourselves in position to deal with the most important part of Chapter 18. And that is the analysis of Bronsted-Lowry acid-base reaction systems, usually from an equilibrium standpoint, in a quantitative fashion. So now we'll see how these reaction equations that we've learned to write and stuff like that can allow us, for any water solution that contains Bronsted-Lowry acids and bases, to determine pH, to determine the molar concentration of every component of the system, which is part and parcel of the acid-base chemistry of the system. Every component. This is a powerful tool. This will require a number of additional considerations. Well, not a number, but some important additional considerations which we have yet to make. And the remainder of our conversation on Chapter 18 will be on this topic. Analyzing in a rigorous quantitative fashion Bronsted-Lowry acid-base systems. And then when we go to Chapter 19, we'll find out that the bulk of Chapter 19 depends on this Bronsted-Lowry acid-base chemistry. And then when we go to electrochemistry, which chapter number-wise is number 22 in our notes, we're going to find out that the bulk of electrochemistry taking place in water solution depends on this. So does it sound like this stuff's important? Ha ha! That's why I wrote important up there. We start with definitions, because some of this language has got to be part of your vocabulary. like Ka and what it is, and Kb and what it is. Keep in mind that from an equilibrium constant standpoint, so far we've learned one specific equilibrium constant by definition. What is it? What's the one specific equilibrium constant we've already learned? Kw. Now to that we're going to add Ka and Kb. Ka. Look at this reaction. This equilibrium reaction. It shows an imaginary hypothetical acid HX reacting with water to make hydronium ion and the conjugate base of HX. If I write the equilibrium constant for that equilibrium reaction, here's what I get. Here's an imaginary base, X minus, which of course is the conjugate base of this imaginary acid HX. Reacting with water, establishing the equilibrium involving as products HX and hydroxide ion, for which the equilibrium constant is this. By definition, the equilibrium constant for this reaction is Ka for HX. By definition, the equilibrium constant for this reaction is Kb for X minus. A acid, B base. Statement. Ka values for reactions taking place in water solution. This is all in the notes. Ka measures the strength of the acid in question to react with and protonate what? Water! And nothing else. Just like Kb measures the strength of a base in water solution reacting with water and extracting H plus from water to produce hydroxide ion. Keep that in mind. Ka, the acid is reacting with water, nothing else. If you change to something else with which the acid reacts with, you're going to change this K value. Same with Kb. So with that, before we proceed, I'll ask you about question 1811. Look at the acid-base table. We've already reminded you that chemists have done novel Bronsted-Lowry acid-base studies in solvents other than water. One such solvent is liquid ammonia. If I measure Ka values for acids, like the acids listed on our table, in liquid ammonia, not water, what will happen to these Ka values magnitude-wise? Will they stay the same, get larger, or smaller?
Larger.
They will get larger because?
Ammonia is a stronger base than water.
Ammonia is a much better proton grabber than water. The formation of ammonium ion is much easier than the formation of hydronium ion, because ammonia is a much stronger H plus grabber than water. Acetic acid, for example. We know, as the table shows us, that strength-wise acetic acid is a weak acid. And if we write a reaction equation, HAC plus water, to make hydronium ion and acetate ion, we've now written a reaction equation which by definition corresponds to Ka acetic acid. And on the table you see this to be 1.8 times 10 to minus 5. If acetic acid reacts with ammonia, however, as products we make ammonium ion and acetate ion. What's the extent of that reaction? Large or small? Acetic acid reacts with ammonia, making ammonium ion and acetate ion as products. Does that reaction go to large or small extent? Large or small? You remember running that reaction in 2045 laboratory, assignment 4? Huh? Do you remember that when you mixed acetic acid solution, which in assignment 4, conductivity studies, you found out that the solution was not a very good conductor. And you measured the conductivity of ammonia solution, not a very good conductor. But when you put ammonia solution and acetic acid solutions together, which individually are neither good conductors, you wound up with a solution that's an excellent conductor. Because ammonia and acetic acid react with each other to a large extent to make ions as products. Ammonium ion and acetate ion, and that's why the resulting solution is a damn good conductor. Because Ka for acetic acid and ammonia is a big number. Now, let's finish by showing you something that's in the notes, but it's important, so I'm going to repeat it. Notice here I've rewritten the chemical expression of Kb for X minus right here. Now I'm going to play a game with this Kb for X minus and multiply it by hydronium ion molarity top and bottom. What does that do to the numerical value for Kb? Nothing. Because that's multiplication by 1. But let's see what this multiplication by 1 achieves. First, it gives us the hydronium ion hydroxide ion concentration product for an equilibrium system. What is this? Kw. Now let's look at what's left. HX molarity up top, X minus molarity in the denominator, times hydronium ion molarity also in the denominator. What's that correspond to? You see that? What do you get if you take this Ka expression for HX and invert it? You get that, don't you? How about that? So for the hypothetical acid, HX, and its hypothetical conjugate base X minus, we've now established this relationship, which means Kw is equal to Ka for an acid times Kb for the conjugate base of that acid. This tells us something that's important. Here's the important part. You see in our acid-base table we've listed some Ka values? In fact, we've listed all the Ka values for all the acids in our table, which are as strong as or stronger than water, but not as strong as nitric acid. Hydronium ion all the way down through water. These Ka values are listed. Do we need also to list the Kb values for the conjugate bases of these acids? Hell no, because now we know how to calculate them. And we'll pick it up from this point next time.